Hi, hello everybody. We are going to continue on in chapter 6 today with kinetic energy and the work-energy theorem. We mentioned kinetic energy a little bit, very briefly in section 1. I'm just going to have a bigger focus here. And in chapter 7 we'll learn a lot about other kind of energies as well. But for right now, one simple thing that we should know is, one, kinetic energy is known as the energy of motion. So if something is moving, it has kinetic energy. And for any given moment, the kinetic energy of an object is equal to the formula 1/2 mv squared, 1/2 mass times velocity squared. I noted on the last lesson from section 6.1 is that energy, not just kinetic, but all energies and work are measured in joules, because work is just really a form of changing energies. And I'm going to go, just to remember, do some review from what work is and tie it in more to kinetic energy. I'm going to go back to old simulation just so I can have something to push on here. So I'm not going to put any vectors on it. That's not our concern right now. My concern is simply if I put, actually I will put one set of vectors on just so you can see when there's a push. Alright, so remember some basic stuff about work. There's a crate sitting on a flat surface, and right now this person is not pushing on it and it's not moving. Remember, when something is not moving at all, there's no work being done on it. Doesn't mean there can't be forces there, because we can see the forces present from normal and gravity, but neither one of those are causing any motion. So number one thing was that something has to be moving to do work on it. And if you do get it to move, I'm going to slowly up my applied force by this person. Once I do get it to move, what I did was I changed its kinetic energy. That's going to be the focus today, okay? So its kinetic energy when it's at rest is 0, because our formula is 1/2 mv squared for this energy of motion, as we call it. So it would have 0 joules of kinetic energy. But once I do a certain amount of work on it, then I give it some kinetic energy through doing work on it. It's just like a connection. It's a chain of process, basically, where the amount of joules of the total work I or something does on that box equals the exact amount in nature of the change of kinetic energy. Right? So, for example, let's use some simple numbers here. One of the numbers is already simple on it. It's a 100 kilogram crate, so I'll use that number that's noted down here. And let's say there's no velocity setting on this, so you know how fast you push it. But let's say I push it from rest up to a speed of, let's make simple numbers, 10 meters per second. Alright? Let's pretend when I did work on that and gave it and changed its kinetic energy, let's say I gave it 10 meters per second of velocity. Right? In that case, it started with a 0 KE because it was at rest. If I plug 100 in for M and 10 in for velocity, I get 100 times 100, 10 squared is 100, and I would take that times a half, or in other words divided by 2, and that means I changed its kinetic energy by 5,000 joules. And the work-energy theorem simply states that the total work done on the object is equal to the delta KE, or change in kinetic energy. A final minus initial, or a later minus the earlier one. My later one, KE2, would be the kinetic energy once I got it up to 10 meters per second. And kinetic energy 1, for my example I'm using here with the simulation, was at rest, so that's 0. So that must mean the total work I did on this block, the total work I must do on it is 5,000 joules using those numbers. Now, the total work, actually, I guess I shouldn't say I did on it, the total work done on the box. Now, what encompasses the total work? It depends what forces are on the axis of the displacement. These forces don't matter, but watch as this guy pushes it. Right now I have friction turned on. So while he was pushing it, I can't pause it while he does it, but you can see that while he's pushing it, there's applied force and frictional force. So not just the man does work on the box in this case. The work total, those 5,000 joules that we could figure out through the change in KE, is the total work between the man and the force of friction, because both of those forces are on the axis where the displacement's occurring. And going back to what we said in lesson 1 in this chapter, the man does a positive amount of work, because the man pushes to the right and the box moves to the right. And if our force is in the direction of the displacement, 100% same direction, then it does positive work. But you notice, as we do work on this thing, that friction is on the axis of the motion too, but it's opposing, 100% opposing the displacement, so it's negative work. And we could break that down if necessary. We could break work total down into, for that particular scenario, the work of the person, the work of the person plus the work of friction. That would be what equaled 5,000 joules. And then maybe solve something from there. And there could be cases where there is no friction. We could turn this to ice or little enough friction where it doesn't matter. And now if this person did the same thing as a moment ago, if he got it up to 10 meters per second while he was pushing it, then that 5,000 joules is only due to the work of the person if there's no friction. But we always have to consider, when doing any kind of work problem, work is always done by any force that is on the axis of displacement. If that force is in the same direction as the displacement, it's a positive amount of work. If it's in the opposite direction, it's a negative amount of work. And don't forget the fact that when we say work or energy, as a matter of fact, when we say it's positive or negative, that doesn't mean direction anymore once we apply it to that. It means that if we do a positive total amount of work on something, that means we gave energy to the system. And in most cases, in many cases, that means we sped it up. But in the case of something like friction that could do negative work on something, that takes energy out of the system. It takes work out of the system. And like friction does, that could cause a slowdown. Alright, so that's really the only new concepts in this section of how work and kinetic energy are related. So just think about it, since you need motion to do work, once you do it, you change its kinetic energy, you change something about its motion, right? So let's look at example 6.3 right now, if you have your books open. This is on page 179. To do a fairly basic example, this actually refers back to the tractor example we did in the last section. It says, let's look again at the sled in figure 6.7 and our results from example 6.2. Suppose that the sled's initial speed, v1, is 2 meters per second. What is the speed of the sled after it moves 20 meters? Okay, so it tells us initially what we're calling v1 is 2 meters per second. We know, referring back to example 6.2, that what we were asked in that example was find the total work done. That was 10,000 joules we figured out. And this is telling me we moved for 20 meters, okay? And actually for this particular example, we won't need the 20 meters that was already figured in the last one to get that 10,000, but I just have a note that that's how far it moved, because that's what this one's new example is referring to. We were also told in 6.2 that the sled and its load was 14,700 newtons. And of course, if we need the mass, which we will, we could divide that by 9.8 because Fg equals mg. And we could get about 1,500. My units look like it got caught up here when I scanned this, so that should say 1,500 kilograms. Kilograms got cut off right there. All right, and it just wants us to find our velocity once it has moved these 20 meters, or at the end of after applying a total force of 10,000, or total work of 10,000 joules. And don't forget that work total encompassed both the pull of the tractor, the horizontal pull, and what friction was doing. That's what encompasses that 10,000 that we did last example. So to find this, we could simply use the work-energy theorem. And the work-energy theorem, which we noted above, states the total work on an object is equal to the change in kinetic energy, where Ke equals 1/2 mv squared. This is like the final or later kinetic energy. This is the initial or some earlier kinetic energy. I could just solve this for V2. That's what we're being asked. Rearrange this thing, and we get 4.2 meters per second. Okay, so before we move on to one other example in this section, a little bit longer one, I want to stop and show you something that's very important right now. Where did the work-energy theorem come from, as well as the formula for kinetic energy, basically? And it actually comes from things we already learned. So I'm going to flip over to my notepad that I could draw on here and really show you the derivation real quick of this work-energy theorem. And once we see this derivation and realize where it comes from, we'll realize that we could keep applying the same ideas of Newton's laws as an underlying concept to all these problems. So let me actually start there with Newton's second law. Remember, Newton's second law says the sum of all forces, aka F net, is equal to ma on any given axis, right? And we also, very early in this year, used many kinematic equations. And we had one of our kinematic equations was V squared equals V initial squared plus 2a times some displacement that we might refer to as delta x or delta y. Let me just more generically call it just d. Okay? And if I solve this kinematic equation for acceleration, I would get v squared, some final velocity, minus v initial squared over 2d. Since a equals that and a is in Newton's second law, I could sub it in there. So I perform that substitution and I get the sum of all forces equals, remember, sum of all forces on the axis of the acceleration equals m times v squared minus v initial squared over 2 times d. Basic substitution with two formulas we've used for a long time, right? Alright, next I'm going to just rearrange this a little bit. Alright, I'm going to distribute the mass through the term in parentheses. And at the same time, I'm going to multiply d to both sides. And now you might notice something coming into play here. And now I could write this really what I have right now is the work-energy theorem. Remember what work is: a force multiplied by a distance. Forces that are on the same axis as the displacement, right? Which isn't that how Newton's second law defines the forces? The same axis as the acceleration, therefore that axis of acceleration that the total or sum of all forces on would also be the axis of the displacement. Therefore, what this statement really means is, since there's a sum of, is the work total. And look to your right. These terms over 1/2 is the same as 1/2 times them, right? Or kinetic energy, 1/2 mv squared minus 1/2 mv initial squared. And that would be the same as KE2, some later KE minus some earlier KE we could refer to as KE1 like we did in the work-energy theorem. And then we could condense it down to delta KE. So basically, guys, the work-energy theorem is nothing but two old equations you knew that we subbed together. And eventually we decided to call this kinetic energy because it's the energy when things are moving. And this got known as the work, or the work total in this case. So what that means then is, since the work-energy theorem came from old stuff, it's typically possible to solve all these work-energy problems using Newton's second law and kinematic equations separately. So the question then is, why are we using a new method? Well, one is it streamlines the process. All right, it kind of immediately condenses that substitution of equation into one, and we just rename them with works and energies. But a better reason than that, and you won't notice it till a little bit later, but remember, work and energy are scalar quantities. They don't care about direction. We don't have to consider direction with them themselves. And with certain problems that have changes in direction, it's easier to do it through the eyes of work and energy than to go to straight Newton's second law, where you're still dealing with forces directly, which are vectors, and the axis of acceleration. With certain types of motion, when there's a lot of change in direction, like even like an arc-like motion or something like that, you'll see, it's better to take the view of work energy, even though it does really come from all that. Okay, but the main thing is the work-energy theorem really does come from past stuff, Newton's second law. And before I move further, I want to point out another thing. Now that we know that, we can apply thoughts from the past, especially of Newton's first law. Let's say I want to push an object, and I would like to go back real quick to my simulation screen. Now, this simulation isn't made for this, so I'll try to do it the best I can. Let's say I want to push, oops, I need friction back on, sorry about that. I want to push at a constant velocity. We should know, there we go, that looked pretty constant right there. We should know from the past that if you want to slide something at constant velocity when there's friction, which there was, your applied force has to balance and equal out with the kinetic frictional force. That's basically what Newton's first law tells us, right? If objects moving at constant v, they will remain moving at constant v as long as you don't have an unbalanced force. Therefore, if I balance it, it will remain constant, right? And let's apply that idea to pushing something with friction at a constant velocity. Just imagine like sliding your book across the table at constant v, like that. To accomplish that, you have to push at the same, with the same amount of force, as friction is opposing you, as kinetic friction is opposing you since you're sliding. So I'm going to flip back to here, and let's see what that shows me. All right, if I push something at constant velocity, KE2 at any given moment and KE1 are equal, right? I'm just going to take this formula down here. Let's make it up. Let's say as this person pushed on that block, on that crate for 3 seconds. And for 3 seconds, it moved at, I don't know, 5 meters per second. All right? Well, remember, change in KE, KE2 minus KE1, is this, each one of those is the same formula, other than a velocity here and a velocity here. But if I'm pushing constant, a final velocity and an initial velocity are equal, right? When I started pushing constant, again, let's use 3 meters per second, and when I continue pushing constant, 3 meters per second. If those are the same, therefore I'm pushing constant, then I have the same KE2 as KE1. And that means the change in, when I subtract them, 0. So that means the work total is equal to 0. 0 joules. And you might say, well, how is it equal to 0 joules? There's work being done, right? Yeah, there is, but there's work being done by the person, okay? And the person's work, well, the work total for this example of pushing the crate with friction, the work total is the work of the person, I'll just put work P, plus the work of friction, right? And that equals 0. So we could break that down even more. The work of the person is F times the displacement. Now remember, I told you your textbook uses S for displacement. You could use S or D. I don't really care, okay? I use D above, so I'll use it here. All right, so the force of the person times the displacement of the box plus, actually, let me take that away, minus, because at this point we should know friction is doing negative work, so we subtract it off, all right? So we should change that sign to minus now that we've identified it's friction doing the other amount of work that goes into the total. And that's the force of, in this case, kinetic friction times the displacement. And as we said from what we knew before, that's got to, those two forces have to be equal. And if they're accomplished over the same displacement. The reason why they have to be equal is because we push at constant V. If we have this box that we were pushing on, if the person pushes harder than the friction does in any given direction, then we won't be constant anymore. We learned that a long time ago. Remember, it's like these two forces play tug of war. But if we're truly pushing constant, then they're equal and they balance. And that's why the total becomes 0. The person is not doing 0 work. All right, that's not what we're saying. The friction is not doing 0 work. Combining them, their work essentially balances out to maintain a 0 kinetic energy, change in kinetic energy, meaning we're moving at a constant speed. All right, so those are a bunch of old concepts intertwined with the aspect of work and change in kinetic energy. And that's the Work-Energy Theorem. So those are things to think about as we go through this final example here. So flipping back to the notes. There they are. Let's take a look at example 6.4. It says forces on a hammerhead. This is on page 180. Now there's a better diagram in the book than mine, so please look at that and we'll refer to my simpler one to get a good idea what's going on. Look at the one in the book. It says a 200 kilogram steel hammerhead of a pile driver, that's the orangish object in the picture in the book, is lifted 3 meters above the top of a vertical I-beam being driven into the ground. The hammer is then dropped, driving the I-beam 7.4 centimeters deeper into the ground. The vertical guide rails exert a constant 60 Newton frictional force on the hammerhead. use the work-energy theorem to find first the speed of the hammer just as it hits the I-beam. That stuff right there. And it stresses use the work-energy theorem, and that's what I want to stress too once I assign problems dealing with using work-energy theorem. Remember, since the work-energy theorem came from the substitution of a kinematic equation into Newton's second law, you could do this another way, just thinking solely in those terms. But we want you to practice and get used to using the work-energy theorem in this chapter, so please use it, and no other method. All right, so we're dropping. I have like a before and after picture here. In my picture, this little rectangular block is the pile driver, okay? Hammerhead, I should say, that's dropped, and it's going to fall through something on rails that promotes constant friction. And here's your I-beam. Now, in my before picture, I have a little marking on my I-beam right here, this vertical, or horizontal line, excuse me. That just is a reference to driving it into the ground, okay? Because this is going to hit and it's going to drive it down a certain amount. So after it hits, it drives down, and it tells me that the I-beam drives down 7.4 centimeters, or in other words, 0.074 meters into the ground. Not very far, just a little bit. That's like the point of a pile driver, or like pounding a stake into the ground even in a similar way, is that usually if it's something hard to pound into the ground, you hit it over and over again, because every hit, it only goes in a little bit, right? So a little common sense there for our thinking. And we know the other displacement given was how far this hammerhead fell from where it was dropped to when it hits the I-beam. So I'm going to call that displacement S, and I'm going to put a subscript on this displacement so we don't get them confused. S sub I is the displacement of the I-beam into the ground, right? And it tells us the mass of the hammerhead was 200 kilograms, so we could find its weight because we're going to need it anyway, 1,960 newtons. All right, so for part A, we just want to find the speed of the hammerhead when it hits the I-beam. So that's the first part of this problem, not after, the moment it touches it. So in the before diagram, from here where it's dropped to right when it gets to the I-beam. And it was told we're going to use this displacement for that part. 3 meters it fell. Okay, it displaced. During that 3 meters, remember we're using the work-energy theorem here, which says the work total equals a change in KE. Well, first of all, let's worry about the left side, the work total. What is doing work on this hammerhead as it falls? Not after it hits the I-beam, up to the point when it exactly hits it. Well, gravity's doing work on it, on the hammerhead. And friction is as well. Which way is it falling? Downward, right? So the work on the hammerhead is actually the work caused by gravity right here. Okay? So remember, work is equal to force times displacement, as long as we don't need the cosine theta, as long as the force is in the exact same direction axis as the displacement, right? So gravity, we know its force is downward and displacement's downward, so that is a positive amount of work gravity is doing on the hammerhead, right? But friction is acting on the hammerhead as well, but the friction is opposing it, right? It's on the same axis, but it's opposing the displacement, so we put a minus in the total because it is a negative amount of work times the same displacement, because the whole time it falls, it's feeling those effects of friction. So the work total, we have enough to figure out. We could figure out by the numbers we have given that the total work on this hammerhead is 5,700 joules. And therefore, through the work-energy theorem, that total amount of work equals a change in KE. Well, initial kinetic energy is 0. KE1 is 0 because it's at rest. It was dropped, right? Not moving, can't have any kinetic energy. And what we want to find is the V2 in KE2, 1/2 mv2 squared. So we set that equal to the total that we found, 5,700 joules, and simply solve that formula for V2. We get out that the moment it strikes it's at 7.55 meters per second. And we could have figured this out through the combination of Newton's second law with the correct kinematic equation. You know, that's what this really does in a streamlined effect, don't forget, as we proved a moment ago. What I could have done, I'm not going to do step by step, but what I could have done in part A here is used F net equals MA. F net would have been the weight minus friction, without the displacements involved, equals MA, and I could have solved for acceleration. And once I found the acceleration, I could have used the kinematic equations in the form of the free fall equations to find the final velocity. Right? This all does that in kind of one step, basically, in one equation, one formula. So again, that was one reason it's better, and we want to practice the new way, right? And there will be future problems that where directional changes occur, where the work-energy theorem will be much better for other reasons as well. All right, so moving on to part B, we also want to find the average force the hammerhead exerts on the I-beam. So now this is the after part, okay? And we're going to use the work-energy theorem again, but we need to realize a couple things. Once we impact is the first most important thing. So I have a free body diagram to identify forces involved on impact. All right. Once we impact, well, weight of the hammerhead is still down. All right. But once it hits the I-beam pushes back up on that hammerhead with a normal force. And friction is also still there because we're still in those rails that's guiding the hammerhead, and it's still opposing the motion of the hammerhead, so it's upward. So those are all the forces that apply upon impact. Right? It then drives it down into the ground, a certain displacement, 0.074. So remember, what we were asked was to find the average force the hammerhead exerts on the I-beam. So that would be the normal force. Because why? Because the I-beam has to push back up with that same amount so the hammerhead doesn't break through it, right? So that's why normal force is what we're solving for. So the work total for this part becomes the total of all the forces times the displacement. You could do it all together and think of it as F net times the displacement, because F net, I'm calling down positive, by the way, and up negative. Okay, just because I'm going with the way I'm moving. Originally I'm calling positive. All right, if you want to change that, that's fine. You just might have to adjust some other things, but go with me with my directional aspect here. So my net force, which is weight minus friction minus normal force, because those two are pointing up, which I define as the negative direction, times the displacement in this section of the problem is just going to displace that small amount of 0.074 meters that we converted up here in the givens. Another way you could think about it, it doesn't matter, it's the same thing, is each individual force along with its direction times the displacement S sub I. All right? This and this, hopefully for easy mathematical reasons, you could see both mean the same thing written in a different way. Either way, that means the work total. And the next thing we have to do is realize that upon impact, a value I found in part A becomes my initial kinetic energy in part B. I found the fact that the total work as it falls on this hammerhead was 5,700 joules. All right? And all that 5,700 joules through the work-energy theorem transfers to its final kinetic energy, which remember is also in joules, so also 5,700 joules, which created that 7.55 meters per second of velocity we found. So the kinetic energy on impact initially for part B is really the final kinetic energy from part A. It transfers over. Then it drives a little bit into the ground and comes to rest again. So my KE2 is 0 this time. And that's what I'm going to plug into the work-energy theorem. Right? I'm going to plug in this expression for the total work because 3 forces are involved on the axis of the displacement. So they're all giving some amount of work in that total. Equals a change in KE, where we just said KE1 is 5,700 and KE2 is 0 because it comes to rest once it's driven into the ground. And my goal was to find the normal force, or in other words, the force the I-beam exerts, or the hammerhead exerts on the I-beam, or you could look at it through Newton's third law, that would also be the force the I-beam exerts on the hammerhead. It goes both ways. For every action, there's an equal and opposite reaction, right? So we have to solve for the normal force to answer this question. At this point, we just do the algebra. We have all the numbers, we pop in those numbers, and we figure out it's 79,000 newtons. That's big. But you got to consider the fact, what are we doing here? We're driving a large I-beam into the ground using a POW driver. And yes, you better get out a big force else that I-beam's not driving into the ground, right? So a little bit more complex of a problem, but the ideas are all the same. So that ends everything for section 6.2. As always, guys, there will eventually be a time when you guys will ask questions on this stuff, any problems I give. However, do not forget that every Tuesday and Thursdays I post office hours. Alright, and I post them in the morning all the time when they are. It's typically 2 to 2:30, but even if I change the times, they're always going to be there. Okay? So please make sure, if you're struggling with anything, see me during office hours on Zoom through the link on Classroom. Alright, I'm going to post this video with some problems out of this section. At this point in time, the rough idea for the test on this stuff, we still got a couple sections to go, but my goal is to have a test next Tuesday on this stuff. We got 2 more sections to cover. Have a good day.